Your razor might do the job, but Gillette Labs treats my face like a passion project.
Tell him, Dad.
Let's do another example that doesn't fall on those simple 8-bit ranges of the subnet mask. We're going to use the same IP address, but with a different subnet mask. In this case, it will be 165.245.12.88/26. The first step will be to take the /26 cider block notation and convert that mask to decimal. If we look at our chart, we can find the /26, and we can see that it is the 1, 2, 3, 4th octet, and in that 4th octet, we want to put a 192 decimal. That means that our subnet mask is 255.255.255.192, which is the conversion from the /26. If we look at our chart where it has the /26 or the 192, you can see the number of addresses is 64. And since our IP address has an 88, we can look at the different blocks in those 64 ranges to determine where the 88 might be. And in this case, it's in the range that starts with the block of 64. We'll follow the same rules we had before. If the mask is 255, we're going to bring down that address. And if the mask is 0, we're going to bring down a 0. In this example, we have 3 masks that are 255, so we'll simply bring down the address values for each of those octets. In this last octet, the mask is 192. If we refer to our chart, we can see that we have that range of 64 addresses. We look at our IP address of 88 and determine in which one of those 64 address blocks 88 might be, and it's in the range that has 64 as its starting point. This is what we're going to bring down into the 4th octet, is that value of 64. To calculate the broadcast address, we look at the subnet mask again, and if it's 255, we bring down the address values. If it's a 0, we use 255. In this particular case, our subnet mask does not have any zeros, so we need to refer to our chart. Again, we know that this is the range with 64 addresses per subnet, and we know the .88 fits into that second block. We know looking at the chart that the next block starts with a 128, which means that the broadcast address must be the one prior to that number, so that would be 127. So the broadcast address is 165.245.12.127. And of course, to calculate the first usable IP address, we add 1 to our network address, so our first IP is 165.245.12.65. The last IP address is determined by taking the broadcast address and subtracting 1, so that would be 165.245.12.126. We can perform this same shortcut with any IP address and subnet range. Let's take the example of 165.245.12.88/20. If we look at this address, we take the /20 and convert it to a decimal subnet mask. We can determine this by finding the /20 in our chart. It is in the 3rd octet, and that 3rd octet will be a 240. So everything to the left of that will be 255s, and everything to the right will be zeros. So our subnet mask of a /20 is the same as a 255.255.240.0. You also notice in this chart that the number of addresses in each of these subnets will be 16 addresses. And if we look at our chart, we know that we have an address that has 165.245.12.88. So we need to determine where the .12 might be in our list. That .12 fits between the 0 and 16, so it's this very first subnet that we're going to look at in this particular range. Let's calculate our network address. If the mask is 255, we bring down the address, and if the mask is 0, we use 0. In this case, we have a 255 in the first 2 octets and a 0 in the last octet, so we simply bring down each one of those. Since we're looking at the range that has the .12, and we know that there are 16 hosts on each of these subnets, then that .12 is in that range between 0 and 16, and the first number being 0 means that that is our network address, and so we'll bring that down as our 3rd octet. This means that our network address is 165.245.0.0. To calculate the broadcast address, we look at every place there's a 255, and we bring down that address, so that would be our first 2 octets. And if there is a 0 as part of the subnet mask, we use 255, and we'll bring down that 255 for the 4th octet. Since we have a 240 as the subnet mask in that 3rd octet, we need to look at our chart again and determine what number we would bring bring down. Since we know there are 16 addresses in each of those blocks, we know that the next subnet will start with a 16, so one number prior to that 16 would be a 15. And the broadcast address for this subnet is 165.245.15.255. Now we can calculate the first available IP address by looking at the network address and adding 1. That would make it 165.245.0.1. And we can calculate the last available IP address by subtracting 1 from the broadcast, and that would be 165.245.15.254.
Now that I'm a mom, things are different. Verizon's different too. They let everyone in my family choose different plans. We get what we want and we save money. Love that for me.
Wow, every time.
Yeah, every time.
Let's go through the process again with an IP address of 18.172.200.77/11. First thing we're going to do is convert that /11 to a decimal mask, and if we look at our chart, we'll find the .11 is in the second octet, and it has a value of 224. So our subnet mask is going to be 255.224.0.0. On the same line as that subnet mask is the number of addresses, and you can see in this particular example, there are 32 addresses per subnet. Since that /11 is in the second octet, we're going to look at that IP address to determine where it fits in those blocks of 32 IP addresses. So if we were to look at our chart of these 32 address blocks, we know that 172 fits in this range between 160 and 191. So to calculate the network address, if the mask is 255, we're going to bring down the 18 that's in that block. And if it's 0, we're going to bring down zeros. And since this block starts with a 160, our network address is 18.160.0.0. To calculate the broadcast address, if the mask is 255, we bring down the address. And if the mask is 0, we use 255. This means in the first octet, we'll simply bring down the 18. And in the third and fourth octets, where the mask is 0, we'll write 255. In this third octet, we'll go back to our chart, and we know that's the range between 160, and in this case, the next range starts at 192. Therefore, the broadcast address for the previous range would have to be 191. And to calculate the first and last available IP addresses, we will add 1 to the network address and subtract 1 from the broadcast address, meaning the first IP is 18.160.0.1, and the last available IP address is 18.191.255.254. Let's perform one more calculation to see how well we've captured this shortcut. We'll use the address of 18.172.200.77/17. If we go to our chart, we can find the /17 is part of the third octet, and it matches that 128 value as the decimal part of the mask. So if we were to write out the mask, it would be 255.255.128.0. If we were to look at our chart, that /17 is on the same line as blocks of 128 hosts. So we know that there were 128 IP addresses in each one of these subnets. So let's calculate from there what the network address might be. If the mask is 255, we will bring down the address value. And if the mask is 0, we will use 0. To calculate the broadcast address, we look at the subnet mask, and if it's 255, we bring down the address. And if the mask is 0, we use 255. In this example, we have subnet mask of 255 in the first two octets, so we'll bring down those address values. We have a 0 in the fourth octet, so we'll use 255. In this example, that value of 200 is in that third octet, which puts us in the second block starting with 128 and ending with 255. So in this case, the broadcast address would be the last address in that block, which is 255, meaning your broadcast address is 18.172.255.255. And of course, to calculate the first IP address, we add 1 to the network address, making it 18.172.128.1. And we calculate the last IP by subtracting 1 from the broadcast address, making the last IP 18.172.255.254. As you can probably tell, the key to this 7-second subnetting process is being able to reference that chart. So you might want to try writing this down in a chart if you're going to be in a testing center, or you may want to try typing it into a notepad or WordPad to see how quickly you can type it in if you're going to be taking the exam online. If you go to a testing center, you may find that the dry erase pens that they use may not allow you to make a very easily readable chart, so you may want to bring your own pen. Make sure you check with the testing center that it's okay to bring your own fine-tip dry erase pen into the test itself. And whether your shortcut is the 7-second subnetting process, the magic number process, or any other process, make sure you find the shortcut that works best for you and decide to use that for your exam. One of the challenges with the virtual world is we have to somehow take the functions that we would normally use in our physical devices and move it into a more virtualized environment. This challenge exists for our servers and operating systems, but it also exists for our routers, switches, and other networking devices. If we were to break out the different functions of these networking components, we would see there was a data plane, a control plane, and a management plane. If we could take those individual functions that are handled in hardware and create virtualized software versions of each of those, we would be able to deploy this nearly anywhere in a virtual environment. This would not only provide us with a way to create these virtualized systems, but it would also give us additional functionality on the network. If we were to take a switch or a router and look at how that device functions and how it forwards data, we would categorize that particular capability into the infrastructure layer, or the data plane. This is the part of the device that does the heavy lifting. It does the forwarding of traffic, it transfers information from one interface to another, and it provides forwarding, trunking, encrypting, and network address translation. These networking devices also need to reference other data to determine how to perform this function in the data plane. This ability to control where the data may be going is part of the control layer or the control plane. So if you look at routing tables, switching tables, network address translation tables, or anything else that determines how this device functions, it's probably located in the control plane. And ultimately, you as the network administrator will need to manage this device. We do this through the application layer or the
Okay, Martin, I just sent it to you.
Anytime
Private
you
chat.
SSH into a console or control a device from a web-based front end, you're using this management plane. So let's take a physical networking device and turn it into this software-defined networking device. Let's start with a physical firewall. Firewall generally has functionality within it to be able to connect different networks together. We have logic inside that is able to determine how information is forwarded from one interface to another, and we have ways to manage the device on the front console or through a web-based front end. We'll start with all of the interfaces on the front of the firewall where we will connect all of our networks. This is the data plane or the infrastructure layer, and this is where all of the data is forwarded from one interface to another. Inside of the firewall itself, we have tables that allow us to control what traffic is forwarded and what traffic is not forwarded. We might also keep routing tables or switching tables inside of this control plane. And anytime we're managing the device, either by connecting directly to the console or through a web-based management front end, we are using the management plane. One of the ways that we're able to take advantage of this software-based networking functionality is through the use of an SD-WAN. This stands for Software Defined Networking in a Wide Area Network. This is a wide area network that was specifically built to manage the complexities of a cloud-based environment. We've created this SD-WAN because we've changed where we manage and connect to all of the different resources on our network. We used to have everything in one data center, and anytime we needed to access our email or perform a query on a database, we simply access those resources in our existing data center. But now we've taken those email services and we put them into the cloud. We've taken our applications and we've also moved those to the cloud. It's now not quite as simple as connecting to a central data center to gain access to all of our resources, because our emails, databases, and other applications might exist anywhere in the cloud, and that location may change at any time. Here's a view of what we had before the cloud, where all of our services were in one centralized data center. If we had remote locations, we would simply have wide area network links from that remote site to our centralized data center. This made it very easy to set up wide area network connections. That connection was always connected between the remote site and the data center, and that provided everyone with access to the data that they needed. But now we've moved much of that data from our data center into the cloud. So the cloud may have databases, it might have web services, it might have our email access, and these cloud-based services may be located in multiple cloud providers anywhere in the world. SD-WAN was created because we needed some type of wide area network that was application aware. It would know if we were using email, and it would be able to immediately send our data to the closest email service specific to us. An important characteristic of an SD-WAN is its ability to know what application is being transmitted through the network. If it knows the application, it will know where to forward that application data to gain access to an email, a database, or some other application.
So the only person that collected lunch for me so far, oh, I think it's Mr. T. Lord,
We need all
both
of
of
the
y'all got
systems
lunch.
that are connected to this wide area network.
T put his name on the list.
Update themselves anytime there happens to be a change.
So I got 2 people in the next week or so. I got a DoorDash. Look at y'all.
Routers and switches know exactly
Good stuff.
how to reach those services.
Don't worry, it's still open for everybody else retesting too.
Wherever they might be moved. This means
Because what did I say? You have to have
network or anything changes with
A plus
the
by the end of
services,
Net Plus.
our SD-WAN routers will
See, I gave everybody like an additional 3 weeks.
I
said if everybody gets A plus by the end of Net Plus, those people. So we got time. We got time.
Some cloud providers might be accessible through high-speed fiber, whereas others may be connected through 5G or DSL type connections. For that reason, SD-WAN is designed to be agnostic to the transport type. So no matter how you're connected, we'll be able to connect to that remote location. And instead of configuring the policies used for this network through each individual SD-WAN router, we have central policy management where we make all of those changes on one central management console, and those changes are pushed out to all of those SD-WAN routers automatically. So if there are resources in the data center that need to be accessed from a remote site, those locations can still go directly to the data center. But if someone in a remote site needs to access a database or their email system, they can go directly to that cloud-based service using this SD-WAN technology.
With the Amex Gold Card, every meal is a reward. Earning you 4 times membership rewards points at restaurants and U.S. supermarkets.
I believe that everybody's gonna get a cert, at least one.
Every bite, sip, slice, and
It's gonna happen.
whether you decide
So.
to stay in,
How are you doing?
The energy is there.
What is it that you are
The
spelling
lightness
out?
about to
Amex
strike.
Gold Card.
So it's gonna happen. Stay relaxed. We'll be good.
Not all oral care is created equal. The Colgate Total Active Prevention System is engineered to be 15 times more effective at fighting the root cause of oral health problems, helping to improve oral health in just 3 weeks to prevent problems before they start, so you can be dentist ready with Colgate Total.
Many organizations will distribute their applications, their servers, and other devices across many different data centers. Instead of treating each of these data centers as an individual entity, it would be useful if we could have data center interconnection, or DCI, a way to connect these different data centers seamlessly with each other. If you're a service provider, you may have hundreds or even thousands of customers using resources that span across multiple data centers located anywhere in the world. And of course, we use the cloud to distribute our applications to multiple data centers that may be located in many different locations, and those applications may move at any time to any of these cloud-based data centers. When you have devices located in different data centers, however, you may run into situations where IP addressing is very different across those different data centers. There might be one IP addressing scheme for data center A.
What might have thrown a lot of people off too is that inside of
The connectivity
Inside of a
data
router.
centers may also be
I just
very
talked about
different.
this.
Some data centers may be in
Inside of a
large
router,
metropolitan area
you can do what
with
they call a
lots of
screen
fiber
subnet and a
connectivity and
DMZ
large
setting.
amounts of bandwidth. Other data centers
It's
might
on the
connect through
inside of the
network
router.
Ethernet or other types of copper-based
In the
connectivity.
configurations,
The
you click the
applications
box
that
that
are
says
residing in these data
DMZ,
centers shouldn't have
and
to
you can
worry about
create
connectivity
another set of
types,
IP addresses or
address
whatever
schemes,
on the
or
inside.
anything
That's
else
how you're
that
able to
should be
connect the
that data center.
Xbox
We
in
should
a
be
screen
able to put an
subnet
application in
in the
any location,
PBQ.
and that application should work without
So,
any type of issue. We need a way to seamlessly
That's actually a
connect
configuration
data centers
inside the
without a
router.
concern
That's how they're
about
able to
IP
get.
address
So don't be
schemes or
confused when you look at it.
underlying
That's what
network
it's trying to
The
formulate and
solution to this
explain
problem
to you.
is a
That
virtual
configuration.
extensible LAN or VXLAN.
And you can
This
set
technology was designed to
a set of
support
IP
thousands of
addresses
different customers
just
all
for the
using
Xbox
same data
on
center
the inside of the
across
subnet
the
you
world.
created inside
You
the
may
router.
already be familiar with VLANs or virtual local
Okay.
area networks.
So
VLANs
that's
are
that whole
designed to span
visualization that
across
we were looking at
multiple
yesterday.
switches
So
at
just
layer
keep that in
2
your back
so that
pocket
you can have
for
different
those that
areas
are
of the
going
network
back to
supporting
test.
the same IP subnets.
Mm-hmm.
Unfortunately, VLANs have a limited scope because they can only support around 4,000 different virtual networks, and they are limited to layer 2.
Yeah, it takes
which makes
practice.
them
Like
routable.
I actually have
We can
a
support up to 16 million virtual
actually have a
networks.
lab.
And those
You could
virtual
do
networks
in
can be
Net Plus to
connected
show
each
you how
other
to do
over
it,
a
like
layer
what's on
3
the inside
network, which makes
of a
it very
router.
easy
Or
to
I
route
might
over
just
the
connect
existing
my
public
router
internet.
because I have one laying
This
around
is
here.
designed for the large
Get into the
virtual
configurations
environments
and
that
show
we've
you
created
how
and
to do
allows
it.
us to support our applications wherever they
So
might
good
be.
stuff.
Let's take a scenario where we have two data centers. In one data center, we have a virtualization server. Inside of that virtualization server is a virtual switch and three separate virtual machines, A1, B1, and C1. In a different data center, we have a similar virtualization server with its own vSwitch and a virtual machine.
And I encourage you to play
B2,
around with your router at
B2,
home.
and C2. And in this example,
Bring
virtual
it up in a
machine
web
A1
browser,
is
get
associated
into the
with virtual
router,
machine
see
A2.
what settings
Virtual
you
machine
have,
B1 is
and it gives you
associated
more of a
with B2,
visual too.
and
That's
virtual
hands-on.
machine C1 is associated with virtual machine C2. This virtualization server is contained within a rack that has a top-of-rack switch that contains a VXLAN tunnel endpoint. In one data center, that VTEP is numbered 1.1.1.1, and in a different data center, there's a completely different IP address for this VTEP of 2.2.2.2. Notice that both of these VXLAN tunnel endpoints will support a VXLAN network identifier, or VNI. You can see there is a VNI 2000, a VNI 3000, and a VNI 4000 in both of these data centers. So the challenge is connecting VNI 2000 in one data center with VNI 2000 in another data center, VNI 3000 in one data center to the other, and VNI 4000 in one data center to the other. The way that we would accomplish this is through the use of a VXLAN tunnel. This uses an existing IP network to be able to provide the transportation, and we're able to encapsulate information in one data center, send it through this tunnel, and decapsulate it on the other end. Here's how this would work. We have our original frame in the first data center. This is a standard Ethernet frame with an Ethernet header, an IP header, and the payload that we would like to send to the other data center. We're going to encapsulate that original frame within a VXLAN header that sits inside a UDP header, in an IP header, in an Ethernet frame. This information is routed across a VXLAN tunnel, where on the other side it is decapsulated from the tunnel, and the original Ethernet frame is then in the second data center and added to the existing virtualization server. This allows us to connect virtual machines in two completely different data centers, but still have those virtual machines feel that they are both directly connected to each other.
This is the Dell AI PC, built for AI. It was designed to optimize your battery life, so it works longer without a charge, and in places without a charger.
Nature's Bounty supplements your hair, skin, and nails with 2 times the biotin. It's in your nature to glow.
Traditionally, we've always done a good job at protecting the edges of our network. This allowed us to control who may be entering the network and who might be leaving the network. But once you're on the inside, all of the network tends to be very accessible. This obviously creates security concerns if you want to be sure that you have the highest level security on your network. In recent years, many companies have transitioned to more of a zero trust approach. This is a holistic approach to security that affects every user and every application being used on the network. With zero trust, every user, every device,
I'd probably do
every
that now
application is inherently
in
untrusted.
net
We
because
want to check and verify
when we get
any type
into
of
Security
traffic going
Plus,
over our network
I was talking to
to
Martin
ensure
about
that
this.
only
We're going to
the
be
right
working with the
users are
VMs
accessing the right type
for
of
Sec
data.
Plus, so
This means
it's
that
better
we'll be
just to do
implementing
it now.
technologies inside of our network, such as
Some
authentication,
SODIM
encryption,
off Amazon
additional
for like
firewalls,
30 bucks.
monitoring of this network, and any other security controls.
Did you already look up the specs and
When
see
you
if it's
connect to a
upgradable?
resource, there's generally an authentication process.
Yeah,
that
look up the
occurs.
model
There's
number of
usually
your
a
computer at
username and password that you
Lenovo.com
have to enter, and there may be additional authentication factors
and then
as
see
well.
if you're what type
Many
of
organizations may
RAM
also
or
create
SODIM you have.
policy-based authentication, and one of the characteristics of that is
And remember the
adaptive
pin
identity.
layout,
Adaptive
how many
identity.
pins
Every
are in the
authentication
SODIM,
process
very
considers
important.
who's trying
And
to
then
authenticate to the network.
if they say you
Is
have
this an individual who's
onboard memory and then they say
or is this a
expanded,
vendor
that means
who's
it has a
working
slot.
with
You
the
can put it
company
in at a
and
45-degree angle and put it in.
we
That's
might
what you're
also
looking for.
consider where
You
this
can put one
person
chip
may
in
be
there.
authenticating from.
It's usually
Are
like,
they located
and
in
they'll
our
tell you what it
local
is,
area,
and you search
or they
Amazon
have to
for it.
authenticate from a different country?
It's usually like
We
$30,
might also
$35.
evaluate the IP address that's in use and the type of connection that's being used during this authentication. And we might want to combine all of those together to determine how
Gotcha,
risky
Martin.
this
Thank you.
authentication process might be. If a user's inside of the building, they may only need to use a username and password. But if they're coming from an unknown IP address in a different country using a VPN connection, we might want to require additional authentication factors. We might also want to add additional rules and processes based on the information we're gathering during this authentication process. If someone is using the correct username and password, but they're connecting at an unusual time of the day from an unusual location, we may still choose to deny that particular authentication. If this same person was trying to authenticate from inside of the corporate headquarters during normal working hours, then instead we may want to allow that authentication. Once the authentication process has completed and is successful, we can trust that that person really is who they say they are. Now that that trust has been created, we need to understand what type of access that user should have. This may depend on the user who's provided the authentication. If they're part of the help desk, they may be able to view the hardware database for the entire company. If they're the manager of the help desk, they may be able to make modifications to that database. And if they're not part of the help desk or managing the help desk, they may have no access at all to that data. We might also want to consider someone's location. If they happen to be in a different country, they might have a completely set of rights and permissions than if they were inside of the corporate headquarters. And if the user is accessing the systems using a laptop that has been provided by the company and we can verify the certificate on that laptop, then we may give them additional rights and permissions. A good best practice for IT security is to only provide rights and permissions to a user that match the requirements for their job. If your job requires that you have read access to a database, then we shouldn't provide that user with any ability to change that database. This means that we would not arbitrarily provide someone with administrator rights just to be able to access a certain type of data.
Oh, get your own kit,
All users
Mr.
should
T.
be accessing these applications with a limited set
Companies
of
don't
rights and
provide that
permissions.
stuff no more.
One of the reasons we don't want to
Unless you
provide
ask for it and then they buy it and you're waiting like 3 weeks to get it. But
is that
I have like my own little kit. I got a kit off Amazon for like 45 bucks.
Is infected with malware,
It's a small little kit with a wrist strap and stuff. Not bad.
Effectively, the malware now has administrative
Something you can
access
take everywhere.
to all of our systems. One of the challenges with providing the right type of authentication and authorization is that users can be located anywhere. Some users may be located in the corporate office, others may work from home, and others may have a field service position which takes them across the world. And the applications that we use may be located on a public cloud, across the internet, or they may be in our private data center. We need some way to provide a secure mechanism for communication regardless of where the user happens to be and regardless of where the application resides. One way that we can create this secure environment is through the use of SASE. This stands for Secure Access Service Edge, and you can think of this as a next generation virtual private network. This moves our security technologies into the cloud itself, very close to where the application data might be. And we would have a SASE client installed on every user's device, so no matter what system they're using or where they happen to be, they're able to take advantage of this secure access service edge. At the top of this SASE diagram is a public cloud, data center, software as a service, or an internet connection. This is where our applications reside. Our users may be at our corporate office, they may be working from home, or they may be mobile users. As the users are accessing these resources, we're able to provide network as a service, so there's quality of service and routing that we can provide. We might also have security built into this. Zero trust network access, firewall as a service, and DNS security are just a few examples of what SASE can provide. And because the SASE clients are installed on all of the devices and these connections are made automatically, the users don't have to worry about turning on or turning off this SASE functionality. The users simply use the devices they've always used, they connect to the applications that they need to access, and security is built into the entire process.
Waiting on products wastes time and costs you money. Grainger has what you need when you need it. Visit one of over 250 branches or order with next day delivery options to help get jobs done faster. Call, click Grainger.com or stop by. Grainger, for the ones who get it done.
Now that I'm a mom, things are different. Verizon's different too. They let everyone in my family choose different plans. We get what we want and we save money. Love that for me.
Infrastructure as code, or IAC, is a concept where we can take a piece of networking technology and describe it in terms that are best described as code. This means that we could build a configuration file that could accurately describe everything in our infrastructure. Every server, all of the network devices, firewalls, switches, routers, and all of our applications can be configured as this code. This means instead of manually building, installing, and then configuring all of these devices, we can do all of that work inside of this code and then simply tell the cloud to build out all of these systems to our specification. We can even use this to create versions of this infrastructure, so we can build out infrastructure as code configurations, deploy that configuration, and then make minor changes and redeploy the configuration, and all of those changes will take effect. This also means that if we need to build another exact duplicate of this configuration in a separate data center, we simply take our code, we move it to the other data center, and we apply that infrastructure as code to build out a completely new application instance that is identical to the original. This is obviously one of the most powerful features of cloud-based technologies, and it allows us to have flexibility in where and how we deploy these systems. This is a very simplified version of an infrastructure as code configuration file. You can see all of the definitions are in here to create a host that's called mail.example.com. This infrastructure as code also includes children devices such as web servers and database servers, and you can see the host names are included in there as well. Inside of this same configuration file, we might want to include other details such as the type of CPU, how much network configurations, IP addressing, the applications that need to be installed, and everything else we need to get these systems up and running. If we can automate the process of building out a series of devices, then we can also automate the process of responding to issues. This is done through a process known as a playbook. A playbook is
Mr. T, for hours, I think you are officially okay at this point.
Or address a particular issue. For example,
During the day for the course, so.
A data breach, you could create a playbook that would step through that process. Or if you needed to recover from ransomware, there may be a set of very well-defined steps, and those steps would be contained within a playbook. This is obviously things that we do manually when we're addressing issues one by one, but putting it into a playbook allows us to automate this process. Perhaps you have a system that identifies the malware. It then references the playbook to know to remove that device from the network, delete everything on the storage drive, re-image the system, and then redeploy that system into your infrastructure. This can obviously be reused over and over again. So anytime you run into that particular issue, you simply apply the appropriate playbook. Playbooks are commonly implemented into SOAR platforms.
Michael.
SOAR, that stands for
How'd you do?
Security Orchestration, Automation, and Response. This is a management console that allows you to centralize the operations of everything you're doing with security in your environment. And if you want to implement playbooks, this would be a perfect console for a centralized deployment and monitoring of those playbooks. This automation with playbooks and with infrastructure as code become very handy when you run into particular situations. For example, you may want to avoid instances of configuration drift where there are minor changes to configurations between different application instances. Or perhaps you want to be sure that all of your systems remain in compliance with a set of standards. We can do that using infrastructure as code. We can make sure that every single one of those systems is created using the same infrastructure as code definitions, and therefore you would have identical systems wherever you deploy them. Or perhaps you're configuring a testing environment and you want to be sure that that testing environment is identical when you deploy it into production. Infrastructure as code would be a perfect choice to be able to completely document what you have in the test environment and deploy that identically into your production environment. And if you want to be able to duplicate this same configuration across all of your data centers wherever they might be in the world, you would obviously use infrastructure as code.
Imagine being able to build anything just by thinking about it. Meet Base 44, a complete AI creation platform made for anyone with an idea.
This would also be valuable if you needed to make a configuration change or an upgrade to an existing piece of software or system you may have already deployed. You simply make that definition change within your infrastructure as code definition file, and then you deploy that to those systems. It will note the difference and make those changes that you need to be able to upgrade those systems. We can also use infrastructure as code to be able to document the configuration that's been made to an existing system. So we may want to scan through a system that we would like to duplicate, have all of those configurations implemented within an infrastructure as code definition file, and then we'll not only have documentation of that system, but we'll be able to duplicate that system at will. As you can imagine, in large environments, these definition files become extremely important, and you want to be sure that you're running the latest version of that configuration file when you deploy these systems. To be able to ensure that level of control of the configurations, you need source control. This allows you to manage any type of change you may want to implement into those definition files, and then you'll be able to test those configurations and then ultimately deploy those into a production state. This prevents many different people from making their own minor changes to a configuration file, and instead you have one central repository where all of these changes are kept. And if somebody wants to make a change, they would need to make that change into your source control system. Sometimes we refer to this as a version control system for that very reason. A very popular type of a version control system is Git. We use that often on the internet to be able to maintain these source codes across multiple users wherever they might be in the world. So you might have this central repository of a production system. You might want to make some changes, and those changes would be tracked and merged together into the final version. There could be many people making their own changes and merging all of those changes into the final config. This means that we can have many people working on these infrastructure as code definition files. They could be making changes to the area that's specific to their part of the build, and then we can merge all of those changes together into one centralized configuration. There might be occasions where one person makes a change to align within the code, and another person makes a different change to the same line within the code. If you try to merge all of those together, there will obviously be a conflict. So your version control software not only needs to recognize these conflicts, but also give you a way to manage what change you would really like to make into the final code. This might be something that the version control software can do automatically, or it may require manual intervention by one administrator who can decide which configuration is really the best one. This change control software also allows us to create branches of different types of code. So we can create a version of an infrastructure as code definition file. We can branch that code off to do our own testing with, make some changes, and then later we can merge that into the original code to create a new version. This allows us to have a production definition and then take that and configure it in a testing environment for upgrades, changes, and optimization. And then once we've tested that, we can then merge it back into the production environment.
This is the newly redesigned Dell AI PC with Intel inside. It's not just an AI computer, it's a computer built for AI. So you can do the stuff that slows you down way, way faster. Like that. And that. And yeah, that too. It's a U multiplier. So you can get more done quicker, which means you get to be done sooner.
It's your bag, sir.
Well, give it away.
Oh, you the Gecko! I filed a claim for my car with the Geico app. Only took 2 minutes.
Well, I mean, car goes all about getting more than just savings.
Next time, how about less fluid ounces?
Fair enough.
Get more than just savings. Get more with Geico.
Our current estimates put the total number of devices connected to the internet somewhere around 20 billion with a B. One of our ongoing challenges associated with this huge rise in number of devices is that IP version 4 can only support 4.29 billion of those addresses. The rest of this, we very commonly use network address translation or other methods to be able to communicate with all of these devices with such a limited number of addresses. And as you may already be aware, there are no more IPv4 addresses to be assigned. We have hit the limit to the number of IP version 4 addresses that we're able to use. We've been able to provide ongoing support for IP version 4 using network address translation. And the internet configuration that you use at home and at your office uses network address translation to be able to connect hundreds or even thousands of devices to the internet using a minimal number of IP version 4 addresses. Although this works with most of the applications that we use, there are certain apps that would prefer not to use network address translation. And this simply creates more complexities and difficulties for those of us that need to communicate over these IPv4 networks. Fortunately, we have a solution to this limited number of addresses, and that solution is a new version of IP referred to as IP version 6. IP version 4 addresses are 32 bits in length. IP version 6 addresses have a 128-bit address, which gives us a much larger address space to use when we're assigning these addresses to all of those many devices on the internet. Another way to visualize this would be to say that every grain of sand on Earth could have 45 quintillion unique IP version 6 addresses. You can see that this larger address space with IP version 6 resolves that IP address constraint that we have with IP version 4. There are a number of differences between an IP version 4 address and an IP version 6 address. This is an IP version 6 address, FE80:5D18:5D18:6FFD:8F52. You can see that is a very different style of addressing than IP version 4, where we were only dealing with decimal numbers and periods. In IP version 6, we are using hexadecimal values, and we're separating those with a colon. If we were to write out that entire address into its entire 128-bit form, you can see that it is completely listed here, and that is a much larger address than we deal with IP version 4. If you wanted to view this in a binary form, you can see that we have the representation of that same address listed in binary. You can see here that each section of an IP version 6 address that we separate with colons is 16 bits in length. You can see the 16 ones and zeros listed in each one of those sections. This also means that each section is 2 bytes in length, and you may also see it represented as 2 octets in length. So in total, the IP version 6 address is a total of 128 bits, or 16 bytes in total. You might see an IP version 6 address written out with all 128 bits being shown on the screen. But you might also see these addresses listed in a compressed form, which makes it much easier to be able to read. When we're using this compressed form of an IPv6 address, there are a number of rules to keep in mind. One of those rules, if there are groups of zeros that are together, we can abbreviate that entire group by simply replacing those zeros with a double colon. We can only do this one time in an address, but usually that's all we need to make this address much easier to read. We also can remove leading zeros from each group within the IPv6 address. Let's take an IPv6 address and perform this compression to see what that would look like. The IPv6 address we'll work with is 2600 colon delta 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 colon 1111 colon 0001 colon 000. You can see the zeros go all the way through to the end to the number 1. Our first rule here is that we can remove any of these leading zeros that might be in all of these groups. This means that our IPv6 address with those zeros removed would be 2600 DDDD1111, and then each of those leading zeros in all of the remaining groups would be removed. You'll also notice that there are 3 individual groups here that are simply zeros. And one way that we could simplify the writing of this IP address is to abbreviate 2 or more of those groups together with double colons. So all 3 of those zeros would be removed, and we would replace them with one series of double colons. This means that we would have a very simplified form of this address. Instead of having all 128 bits of that address shown on the screen, the address is now simply written as 2600 DDDD1111 1 double colon and 1. Let's look at another IPv6 address and perform the same compression. This IPv6 address is 2601.04c3, 4002, BE00, 3 groups of zeros, and it ends with 0066. Our first step would be to remove the leading zeros in all of this. We have our second group has 1 0 in front of it, and there are a number of groups at the end that have leading zeros that we can simply get rid of. You'll notice in this example that there are 3 different groups of zeros that are combined together, so we can remove all 3 of those zeros and replace it with a double colon. This greatly simplifies this much longer address into 2601 4 Charlie 3 4002 BE00 colon colon 66. As you can see, the IPv6 addresses are very different than the IPv4 addresses that we're used to seeing. And because of this, IPv6 and IPv4 cannot directly communicate with each other. Therefore, we need some method to be able to have these older legacy systems that only understand IPv4 be able to communicate on our more modern IPv6 networks. This creates some communication challenges when trying to combine IPv4 and IPv6, but fortunately there are a number of different ways to bridge this gap.
Nature's Bounty supplements your journey with advanced menopause relief to manage hot flashes.
At Grainger, we have over 1 million products, including the ones that help keep your workplace safe and sound. Shop our vast inventory of safety products at Grainger.com. Grainger, for the ones who get it done.
One of these methods would be to tunnel the traffic. We would either tunnel IPv4 within IPv6 or tunnel IPv6 within IPv4. This would give us a way to communicate even across networks that were very different than the protocol that we were using. Another way to bridge this gap would be to use a dual stack configuration where the system that you're using can communicate with both IPv4 and IPv6. And another way would be through the process of translation, where we are converting one IPv4 address into a completely different IPv6 address. Obviously, these are stopgap measures, and they're not designed to be a long-term solution for connecting these different types of networks together. Ideally, the best long-term solution would be for all of us to move to IPv6, and hopefully one day we'll be able to take all of our systems and be able to run them as a pure IPv6 environment. In the early days of IPv6, where we did not have a lot of infrastructure devices that understood IPv6, we did a lot of tunneling of that IPv6 traffic. This was obviously designed to be a short-term use, and these days it's not very common to still see this tunneling being used. One of these tunneling types is 6-to-4 addressing. This allows us to send IP version 6 traffic over an existing IP version 4 network. It creates an IPv6 address based on the IP version 4 address that you're currently using, but it requires you to have a specialized relay router to be able to transfer that data. And one big disadvantage of 6-to-4 addressing is it does not support any type of network address translation. Because of both those limitations and because we have more devices these days that natively support IP version 6, we no longer commonly see 6-to-4 being used, and this functionality has now been removed from all Windows versions. If you can tunnel IP version 6 traffic across an IPv4 network, you can also do the reverse with 4N6 tunneling, or we can tunnel IP version 4 traffic across an existing IP version 6 network. Both of these were used as relatively short-term solutions, and it's very unusual to find 6-to-4 addressing or 4N6 tunneling still being used on our enterprise networks. A much more common method of migration, and one you're probably using on your existing system, is dual stack routing. This allows us to use both IP version 4 and IP version 6 at the same time on the same system. You might have an Ethernet adapter on your computer, and that Ethernet adapter has both an IP version 4 address assigned to it and an IP version 6 address assigned to it. The IP version 4 side works exactly the same as it always has, and all of your applications that use IP version 4 can use that address to be able to communicate onto the network. If you have applications that would prefer using IPv6, they can use the IPv6 addressing associated with that Ethernet adapter. These applications will use the IPv6 address that is assigned to your Ethernet adapter. It will use the routing table within your system for IPv6, which is a different routing table than you're using for IP version 4, and all of the IPv6 settings that are associated are all independent from anything that's happening with IP version 4. This tends to be a very good middle ground because our application can choose IP version 4 or IP version 6, and either one of those will work properly on the network. One of the things that we used with IPv4 to minimize the restriction that we had with IP addresses is to perform a network address translation. We would take our existing internal IPv4 address and translate that into an IPv4 address that can be routed across the internet. We can perform a similar translation to move between IPv4 and IPv6. This translation is called NAT64 and allows us to seamlessly translate IPv4 and IPv6. Just as we need
Is
a
that
specialized
Kevo?
network address translation router when we're using IPv4,
What did he
we
say?
also need
Did he
a
say he
specialized
passed?
router when we're using NAT64. This allows us to
Leah
take a
knows she got
device
the
that
411.
communicates via IPv6, but
She's
still
like, nope.
allow it to communicate with
Brian,
devices
Martin,
that only
y'all
communicate
know.
using IP version 4. The key is in the middle,
Wonder if
we're
Kevin
able to use
passed.
a NAT64 capable router to make that translation change between those two protocols. This also uses a specialized DNS server to be able to translate the DNS request from IP version 4 to IP version 6. This is called DNS64, and it's an important part of the overall NAT64 process. For example, let's say that you wanted to communicate from your device, which is an IPv6 client, and you wanted to communicate to ProfessorMesser.com. Let's assume for this example that ProfessorMesser.com can only communicate using IPv4. The first thing that happens, of course, is we need the IP address of ProfessorMesser.com, so we send a DNS request to our DNS64 server. This server is going to make a DNS request on our behalf to that IPv4 network containing the DNS server that is used by ProfessorMesser.com, and of course that DNS server is going to respond back with the IP version 4 address associated with that server. Once that IPv4 address is received by the DNS64 server, it creates an IP version 6 version of that address that redirects it to the NAT64 router. To the IPv6 client, it thinks it's received the IPv6 address of ProfessorMesser.com, but it's really received the IPv6 address of the NAT64 router. So now when our browser needs to communicate to ProfessorMesser.com, it sends its initial send to that IPv6 address, which is the NAT64 router. That router is responsible for performing the network address translation, where it is able to take the IPv6 address that we use and translate that into an IPv4 address that the web server understands. This process is obviously reversed when the response is sent back, allowing these two devices to communicate to each other, even though one device only understands IPv6 and the other device only understands IP version 4.
At King Soopers, you never compromise. You get up high quality that's guaranteed fresh and down low prices on over 1,000 items. With quality and
the routers that we use in our homes and our offices have an important job of forwarding traffic between one IP subnet and another. It's a relatively straightforward process, although there is a lot of technology under the surface that makes this happen. But if we were to look at this in a very simplified form, we can see that the router is performing a series of relatively simple steps. The first step is to identify what the destination IP address might be for incoming traffic into the router. It looks into the packet, identifies what the destination IP
Should be in the support, or you can look up your Lenovo specs or your model number.
What the
It'll tell
best
you.
route will be for this particular packet. If the destination IP address of this particular packet is associated with a subnet that is directly connected to this router, then the router simply sends the packet onto that local subnet. But in many cases, the destination IP address is on a subnet that is not locally connected to this router. The router will examine that routing table, determine what the best next hop might be, and then send the traffic out that particular interface. This next hop is the IP address of the next router down the line, and when that router receives this packet, it performs the same process again until the packet finally makes its way to its final destination. As you can imagine, that routing table becomes very important, and when we're troubleshooting routers, we refer often to the routing table, what the next hop might be, and determining where these packets should be going once they leave our router. If a router refers to its table and does not find a
that means you do have a slot for SODIMM.
it will simply discard that traffic.
It should tell you what it takes, and then you just order it off of Amazon.
Becomes very important. Let's look at this network diagram. There are 3 separate routers in this network diagram and 3 individuals that would like to communicate with each other. In this case, let's focus on router 1. You can see router 1 is connected to 3 different subnets. We have a subnet 10.10.10.0/24. There's another subnet between router 1 and router 2 that is the 10.10.40 network. And then another subnet between router 1 and router 3, that's the 10.10.50 subnet. Those 3 subnets are directly connected to router 1. So if we were to look at the routing table for router 1, it would see the route for 10.10.10.0/24, 10.10.40.0/24, and 10.10.50.0/24, and all of those networks are locally connected.
Yeah, it's like super expensive on the
problem occurs
Lenovo
if
site.
Sam would like to communicate to Jack. Although router 1 knows about the local network,
You probably have it
there's no
overnight.
idea that there are more networks.
It's like all my students always
outside
upgrade their
router 2
laptops
and
with
router
RAM.
3. And those particular networks of 10.10.20.0/24.
Oh, he can't get overnight in Alaska? You got FedEx right there.
Are nowhere
That's the
in
FedEx
this
hub.
routing table. This
Alaska.
means if Sam wants to send traffic
That
to
UPS,
Jack,
right?
Sam will put this packet out on the network. It gets to router 1.
I would have thought they
Router
would
1
have.
examines the destination IP address of
How many days before you get it?
10.10.20.2, and then looks through its table and realizes there is no 10.10.20 network.
I mean, nothing more than a week though, right?
And the packet
Usually.
is discarded and never makes its way down the network. One way that we could create a more complete routing table is to build it ourselves. This administrative creation of a routing table is referred to as static routing. And if you would like to build static routes as the administrator of your routers, then you will manually be configuring these routes inside of every router that you use. Static routing is a very
Look at Kevin. Here we go.
inside of the router, and if you're managing a smaller network, this
That's
might
a.
be perfect
Is he
way
smiling
to
you?
manage
I
where
can't
the
tell.
routes might be.
He's like,
With
yeah, you
static
bastard.
routing, there's no overhead that you would normally see on a
Congratulations.
dynamic routing protocol. We'll talk about dynamic.
That's water from the glacier in Alaska.
So there's no CPU cycles, there's no
It was
memory
blessed
usage.
by the Eskimo
We're simply
medicine
adding the
man.
route ourselves, and we don't have to do any additional
Too
processing
funny.
to the routing table from there. This is
All
very
right,
common for
congratulations,
remote locations where you might have
boy.
a single
Kevin,
internet connection into that remote site, and all communication
I'm gonna use what Aaliyah
takes
taught
place
us.
over that single connection. We often refer to these as stub
Good stuff.
networks.
What was your,
And because we don't have to worry
what was your
about
score,
any type
if I
of
can ask?
routing updates or
739.
router
Dang, somebody else got a 739. Charles got, Leah got a 7. Leah, yeah. The same score. It's my girl there. Charles got 731. Good stuff.
Configuring a handful of routers with their own
Man,
stack
good job,
routes is
everybody.
straightforward.
Good job.
But if you're managing
So what I would
hundreds or
ask from those who, if we got one more person, and I'm still waiting for it,
configuring
but
a static route in each of those routers
share the
can take
knowledge.
quite
I know y'all have a Discord or
This
something
also
going on.
relies on you adding the correct
Study
routes
groups
to
are good
every
to
router.
do.
There have been times when I configured static routes and I've set
I
up
like
my
to
own
see the whole
routing
class
within
come up
my
with
network
at least everybody. I want everybody to at least have one before they leave here.
And as the name
Minimum.
implies, these routes
But
are static. They don't
let's help
change
each
once
other
you
with
configure them.
study
So if there
groups.
are
Of course,
changes to the
that's
network,
my
you'll need to manually log
that's
into
my
your routers
responsibility
and
to
those
make sure that
configuration updates
everybody
to
gets a
routing
one-on-one
table
and tutoring.
that match the
That's what I get
changes
paid to
your
do.
network. This
However,
also means that there is no automatic
the other side of
routing
me
if
is
something
like I
happens on
like
your
to see
network.
y'all
You will
succeed
need to manually
and do
configure
better than
these
me.
routes if anything needs to be routed
Just like your dad,
in a different
right?
direction.
I'm the fake
So let's
virtual
configure some static routes for
classroom.
router one. We know that we have our
Or
three
figure.
locally connected routes.
I want you to do
but we
better. I
also
want
have
you to
these
win.
additional two routes, one
I like
from
this. I've been
router
teaching
two
for
and
years.
one
I
that's
love
from
it.
router
You know what I'm
three.
saying?
This
So
would be the 10.10
I like to see y'all
network and
win.
the 10.10.30
So
network. So
let's
we
help
might
each other.
SSH into router one, and at the command line, we would begin to add additional static routes. For example, we might tell router one that if it receives any packet coming through with a destination IP address that matches the range of 10.10.20.0/24,
no, the brand doesn't,
send that particular packet to
that's James right there.
10.10.40.2.
No, the
So
brand
if
doesn't
packet
matter.
does come through with that destination that needs to go to the local network that you have
Mary
is
Poppins,
connected
y'all.
to, it will send all of that traffic to the IP
I like
address
that.
10.10.40.2, which is located on router 2.
My laughing
At
face.
that point, router 2 will examine its own routing table and know that the 10.10.20 network is
Before you buy that,
and send
Aaliyah,
that packet on its
remember,
way. We
if
can
you
do
see
the
that
same thing with the
MTS,
10.10.30
anything in the description
network.
says
So we will
MTS,
manually configure a static
maximum
route.
transmission
If any
something,
destination traffic
that means they're
is
fooling you with the data rate.
send all of that traffic to
It's actually half that number.
10.10.40.2,
So
which means all of that traffic will
make
go
sure it
to
doesn't
the
say
router
that,
rate.
and it's real
Now that
low.
we've configured those static routes in router 1,
A laptop for learning cybersecurity. Mainly what you're looking at is the processor and the amount of memory it has. At least one that has a minimum of 8 to 16 gigabyte.
This is the new Dell AI PC, built for AI. It's like a trusted personal assistant. Learn.
And so the reason for that is mainly because you're going to need it for the virtual systems if you're going through the classes.
Every router in the organization. If you have 3 or 4 routers, that might not be a big problem. But if you have tens or even hundreds of routers, you might want to have a more automated way for configuring your routing tables. One way to do that.
Oh yeah, so that's
dynamic routing. Dynamic routing will have the routers handle this process for you, automatically discovering.
512 gigabyte. Yeah, that is fine.
Where the best route might be. This means that you, as the network administrator, don't have to do any type of static route configuration. You don't have to SSH into the router, make any configuration.
And so that is your main memory, but for the RAM that you need for the processor for the system, you're gonna need at least a minimum of 8 to 16 gigabyte.
Remove a router from the network. All of the routers also know that that route is now no longer available. There is
So I am currently going through the classes, so I am a beginner in cybersecurity. So I am learning it. I am not a mentor or I am not an expert in it. So I am basically.
All right, so we're just waiting for.
I am basically going through the certifications.
See what's going on here. Okay, it says.
I can put the Alpha websites in the chat or in my group or in my community
you can
section.
get more if you want. You can buy 32 gigs.
Yeah, I'm pretty much going through the learning process as well.
Usually they don't make 24, but they do.
And just about anyone can learn
Or
it
just
if you're
another
trying to
16
have
gig stick,
a career in this field.
which will give
Just
you
about
24,
anyone can do it.
right?
I can put
So you can go up on the size.
the helpful
But it doesn't have
websites
to
in
be
my
exactly
community or in the
8
chat.
gigabytes or gigabits.
But I am. It would be great if I could do that because it's a good thing to help other people.
Yeah, T's right. If it's too expensive, just do 16. At least you'll have 24 gigs of memory, which is more than enough.
And then updates its own routing table with this new route to 10.10.20.0/.
Wait, Linux Tech. What are you asking about?
10.40.2. We also have another EIGRP update that has come from router 3, and when that update is received, router 1 identifies a new route to 10.10.
Oh yeah, my pleasure. There are a lot of websites that even provide like free courses too that you can do the practice exam.
In real time, behind the scenes, without any type of user intervention.
You can go create a free account, sign up, and they'll teach you and give you all the practice tests and the exam, so you can easily pass it and be certified.
Although it looks relatively straightforward to perform these dynamic routing updates, there's actually a lot of work that occurs behind the scenes. First, the router needs to listen to the traffic that is on the local subnet and see if there are other routers that are sending routing updates that it can use to build its
Oh, so Linux Tech, I was asking, what are you asking? You're asking about what am I currently learning?
Builds its routing table, it needs to inform other routers of routes that it knows. So it will send its own multicast to other.
Oh yeah, that because I saw the text. So what I am currently learning is cybersecurity. So it's information technology. Information technology is just another section of
as a secondary route.
the cybersecurity field is just another section of information technology. So that's what I'm currently learning.
Depending on the protocol you happen to be using. And of course, if there's any change to the network infrastructure, these routes.
There's also a lot of websites that will give you free courses pertaining to the certifications to make it a lot easier for you. And particularly, there's one website that is called Cisco Networking Academy. If you go there, they'll give you all the practice exams or the tests, and so you could make good preparations from there, and then you can go ahead and take the certification test to be officially certified.
Or would you like to be able to make that decision based on the number of hops that a link might be away from you?
So it takes a lot of work to be able to get there, but once you get the certifications, it's a good accomplishment. So that's what I am doing. It takes a lot of hours, and that's what I'm doing.
Protocols are able to make changes very quickly if anything happens to the.
Oh, awesome! You've already passed the Linux Plus. Congratulations to you on that. That is really awesome.
Routing protocol that you're using. And in some cases, we need to take into account.
I saw that as one of the course on the Cisco Academy, and I had it to my cart, so it's something that I can come back to once I have the time. But that is a good accomplishment. That is really good.
Citric environment. So if you have a lot of Cisco routers, that might be a better routing protocol for you. Although EIGRP
and Linux is one of those main network that
EIGRP is also available on
you'll be using a lot too as well.
There are some aspects of EIGRP that are proprietary to Cisco, so you tend to see it mostly in Cisco-related configurations.
You can get good exams and practice tests on Cisco, the Network Academy website, and you can also go to the CompTIA website. They'll give you all the outline of the exams and the practice tests as well.
To converge relatively quickly, and it's also able to identify any loops and prevent those from occurring on your routed network. EIGRP is also very good at identifying other EIGRP-enabled routers and sending updates over a minimum of network traffic. This keeps your network more efficient and leaves your bandwidth available for other applications. If you want a more generic dynamic routing
Oh, thank you for stopping by. I appreciate you very much. One thing you can do also to to get the algorithms going is just to do the thumbs up. That will have the algorithm moving once you start giving the videos like a thumbs up. So the algorithm recognizes that this is something that you guys are interested in or you like this kind of a content. But I appreciate you stopping by, and congratulations on you continuing what is it that you're doing as well.
Tailgates to power game days. And a trailer backup guide. That's the
It takes a lot of work, but I don't mind. Oh, awesome. Thank you. Thank you. I appreciate that. Stop by anytime, leave a comment on any one of the videos, and just let me know that it's you. I appreciate you stopping by.
Through every aspect of OSPF. We refer to OSPF as a link state protocol, which means it determines what the best route is based on uptime and availability between the different OSPF routers. OSPFs can be used to assign costs to an individual link, so certain links may have a higher cost than another. This allows OSPF to make routing decisions based on what the least cost might be. This cost is often associated with how much throughput may be available on a particular link, if that link is up or down, and how long it takes to traverse that particular connection. With OSPF, the lowest cost and the fastest path is going to be the best route to a remote location, and if there are identical costs on OSPF, many implementations will allow you to load balance across both of those links. If you need to route
All right, if y'all had not taken a break, take one.
To other organizations,
Take one.
then you might want to
See you in
use
10
an
minutes.
external gateway protocol such as BGP. BGP is the Border Gateway Protocol, and it's commonly used on our wide area networks and internet connections. Connecting the internet together and being able to dynamically update the routes on the entire internet is a daunting task. And this particular routing protocol was designed with this specific task in mind. Sometimes you'll hear BGP referred to as the 3 napkins protocol because it was sketched out on napkins initially to solve this particular type of problem. If your organization has one or more connections to the internet and you want to be able to dynamically route to those internet sites, then you'll want to use a protocol such as BGP. The job of a router is to evaluate incoming traffic, determine what the destination might be for that traffic, and then send it out the appropriate interface. The router is effectively determining what direction a packet might go to depending on the knowledge it has about the rest of the network. To be able to make this decision about where traffic goes, we need a routing table. And fortunately, most devices have a routing table. The workstation that you're using has a routing table. The servers that you're accessing have.
Oh, you're asking what type of lives is this?
Maintain their own
It's a video documenting my progress of going through the process of learning a new career, and that is currently what I am doing. So this live is separate apart from other lives that I do at different times throughout the day. But that's what this particular is pertaining to. Learning a different career field.
The tie within the router, and in this video, we'll look at a number of ways that tie-breaking process might occur. Let's look at a routing table. This is a routing table.
Yeah, a lot of the times you go to school or you work a particular job or career field, and sometimes it takes a lot of work to learn something else or do something else, and I'm simply just doing that.
Based on a number of networks that were directly connected and routes that were received using the RIP dynamic routing protocol, specifically RIP version 2. If we look at the routing table, the top part of this routing table.
So it's IT. It's basically where the world is going. A lot of computers, the phone technology, and it's an interesting career field to get into.
The first set of letters on each one of these lines corresponds back to a different set of codes that are shown in that legend. For example, you can see the first line of this routing table starts with the letter C, which means that that particular route is directly connected to this router.
My kids can't hide anything from me.
I'm home.
Especially when they've been using toilet paper that doesn't hold up.
Sure.
If we want to see the route that was added using RIP version 2, then we need to find a line that starts with an R. And indeed, there is a line that has an R, which means that everything on this line was created because of information that was received by this router using the RIP version 2 dynamic routing protocol. And you can see there is a lot of information contained within this line. We can make out some IP addresses. There are different values such as 120/1, and it does appear there are even counters here along with information about specific interfaces. Let's break out just this line of information to determine what is contained within this line of a routing table. Let's break out this line of information to see which each one of these provides.
Oh, my pleasure. If me learning something else can inspire someone else to be open and learn something new as well, it's a good thing. You can always learn a different career field or do another job, and if someone else can think to themselves that they can also do it as well, then it's a good thing. I think we all sometimes just need to see someone else is doing it, or just to get the idea that you can also do something else to better your life, even if it takes a lot of work.
You can also see that it's via 10.10.15.
Okay, so how often do I go live? So now I go live. I try to go live at least every day that I am doing.
We also have this
That I am doing doing the coursework or the schoolwork. Apart from that, like if I'm not doing classes, I'll try to go live as well. So basically every day, or I'll put a scheduled time in my community chat. And thank you for subscribing. I appreciate you stopping by and commenting and interacting. Let me know your ideas as well.
Next hop is one that we would reach by going out a specific physical interface in that route.
If you like the video and you like the content, you can also do a thumbs up, so the algorithm knows that you like the video or you like the kind of a content that you're seeing.
To forward this traffic along to the next hop. One of the first things that a router is going to evaluate is where this particular traffic is destined. We need to be able to look at the destination IP address and compare that to the subnet IDs and prefix links that are contained within the routing table. If there's a match, then we'll know where to forward this traffic. This means that this IP address range and prefix link becomes an important...
The career field that I'm currently learning is information technology, IT, and specifically cybersecurity. So it mostly has to do with computer and machine learning.
You find that there are multiple routes listed to a particular subnet, but there might be different prefix links in each one of those lines. So you might need to evaluate each individual line of a route.
Thank you. I appreciate you stopping by.
Most specific for this particular route.
Thank you.
For example, let's say that you need to communicate with.
Give the video a thumbs up so you could so YouTube knows that you like this kind of a content.
Different routes that would match that particular IP address. One of them is 192.168.0.0/16. The other is 192.168.1.0/24. And the third is 192.168.1.6/32. All of these would be valid routes to that particular destination, but only one is the most specific. We need to evaluate not just the subnet ID, but also the prefix link to determine which one of these is the most specific for that particular destination. And if we were to look at 192.168.1.6, we would know that 192.168.1.6/32 would be the most specific route. In fact, that is the most specific route because a /32 is specific to an individual IP address, in this case, 192.168.1.6. Now, if this route was not in our routing table, we would have to choose between 192.168.0.0/16 and 192.168.1.0/24. The /24 is the more specific route than the /16, so we would choose the middle route if we had a choice between those two locations. This can get even more complicated if your routing table happens to have identical routes to a location that go to different next hops. How do you know which next hop would be the correct one if everything else was identical? And the one way that you would be able to make that determination is by examining the administrative distance. Different routing protocols are assigned different administrative distances within the router itself. This allows the router to pick the best route.
Oh, Capital One? My team's transformer-based AI model,
built using contextual data, helps personalize your experience in real time.
That's how we start. That's technology at Capital One.
Based on the type of protocols or the type of information that it has received. For example, if this is a local connection, it is physically connected to the router, this is the best possible way to get to that subnet, so it has an administrative distance of 0. As you can see here, the lower the administrative distance, the better the route might be. If you have manually configured a static route, the router assumes that you must be the most knowledgeable person for that particular route, so static routes have an administrative distance of 1. If this route was added to the routing table using EIGRP, the administrative distance is 90, and if you receive this route via OSPF, the administrative distance is 110. You can see that other dynamic routing protocols and methods are listed in this table with the appropriate administrative distance for a Cisco router. In some cases, the routing protocol itself may be in a position where there might be duplicate routes to a particular location, and the routing protocol has to make a decision on where the best route might be. In that case, we will want to look at the routing metric to be able to break that tie. Routing metrics are an internal value that are used by the routing protocol itself. So BGP has its own set of routing metrics, OSPF has a completely different set of routing metrics, and EIGRP uses its own set of routing metrics as well. This means that you can't compare routing metrics across different routing protocols. The routing metrics used for BGP are very different than the routing metrics used for EIGRP, and there's no way to compare or contrast those routing metrics across routing protocols. But similar to an administrative distance, BGP might create its own set of routing metrics to a particular site, and then it can determine what the best route might be based on its own internal set of routing metrics. For example, the routing metrics for BGP might be 1 or 2. It will choose the route for 1 because that is the lowest routing metric. Let's look at our routing table for RIP version 2 again. We have that one line in the routing table, the 10.10.30.0/24. It has an administrative distance of 120 because it is RIP version 2, and it has a routing metric of 1. RIP uses the number of hops to a location as its routing metric, so we know that this particular destination is 1 hop away. To be able to reach that particular network, we would go to 10.10.50.2, and we would get to that particular location by sending this traffic out serial 0/3/1 on this router. If you were to use a different routing protocol, for example, EIGRP, you would have a very different routing metric. Here is the same routing table to the same location, but we've enabled EIGRP instead of RIP2. You can see this line in the routing table was created with the code D, and if we refer back to our legend, we can see that D does refer to EIGRP. Everything in this line is very similar to what we saw with RIP version 2, although you'll notice the administrative distance is different. It's a 90 because EIGRP has a higher priority in its administrative distance than RIP version 2, but you'll notice that the routing metric that is determined by EIGRP is very different than the routing metric that we saw for RIP version 2. RIP version 2 uses the number of hops, whereas EIGRP has a completely different calculation that it uses to determine what the best route might be. As you work more with routing tables and begin evaluating these routes on the fly, you'll become much more comfortable with determining where the best next hop might be for a particular packet. One of the challenges we have when working with routers is that there's only one best route to a different location. If you were to look at the IP configuration of your device, you'll notice that you have a default gateway. That default gateway is your local router that allows you to communicate outside of your local IP subnet. But you'll notice that there is only one IP address available to list as the default gateway. You can't list multiple gateways in that list, and this brings up a challenge, especially when you'd like to have redundant routers on a single network. One way to provide redundancy, even though you only have places for a single default gateway, is to create a virtual IP address for the router that's
coming back to break mine.
We refer to this virtual IP as a VIP. And the idea is that if the primary router disappears, we can move that virtual IP to another router on the subnet so that you don't have to change everyone's workstation to maintain the uptime and availability of the network. This means you as the end user may have no idea how many different redundant routers might be on your local subnet. And if the primary router on your network was to fail and the virtual IP address was to move, you would seamlessly continue to have connectivity using that redundant router. Here's how this would work. You as the end user would communicate to a router or a default gateway on your network, and that default gateway gives you access to other subnets or allows you to communicate out to the internet. In this particular example, we're going to use the first hop redundancy protocol, or FHRP, in conjunction with a virtual IP address that we've associated with router 1. This is our active router. Also on this same subnet is a standby or backup router. That's our router 2. Our default gateway is going to be associated with the virtual IP address that we've got associated with router 1, and that means that all of our traffic will flow out of our network through router 1.
Spending time with the ones you love is priceless. That's why Kroger Delivery, proudly serving King Soopers, makes grocery shopping effortless. Get $20 off your first order. We'll deliver your groceries in our refrigerated trucks and bring them to your door. King Soopers, fresh for everyone.
Look, I think something's happened to us.
What are you?
It's me, Mom.
You're not my mother.
Yes, I am.
Get away, you clown freak!
Don't you use that tone with me.
Oh my God, you are my mother.
And you're not who you think you are.
Look at me.
I know, we seem to be inside.
I'm old.
I beg your pardon.
Oh, I'm like the
If router 1 was to fail, there would need to be some type of method to fail over to router 2. But router 2 has a completely different IP address. In this configuration, router 1 and router 2 are always in communication with each other, but if router 2 suddenly realizes that it's not able to communicate with the active router, it then removes that as the active router and becomes the active router itself. Then it takes control of that virtual IP address so that everyone on the network is now able to communicate out to the internet through router 2 using that original virtual IP address. All of the traffic will flow just as it normally did, and the end user has no idea that it's now using a completely different router to be able to perform that communication. Another interesting characteristic of switches and routers is that you can assign multiple interfaces to a single physical interface. We refer to these as sub-interfaces. So even though there might be a single Ethernet interface on a router, we can take that single Ethernet interface and separate it into multiple virtual interfaces. For example, we might have a trunked connection that has multiple IP subnets connecting to a single physical connection. But we may need to reference each individual VLAN in a trunk with a separate IP address on our router. We do that by assigning that physical interface with an additional parameter called a sub-interface. So although the physical interface on that router is referred to as Ethernet 1/1, we would have separate sub-interfaces within that physical interface that might be called Ethernet 1/1.10, Ethernet 1/1.20, and Ethernet 1/1.100. This means that we can set different configurations for each of these sub-interfaces so that we can reference them with the appropriate IP address for that VLAN. Here's how this would look on a network configuration. You can see there are 3 devices. All 3 of these devices are in separate VLANs. There's the red VLAN, the green VLAN, and the blue VLAN. And of course, they're connecting to separate physical interfaces on a switch. The switch then has a single cable between the switch and the router, and it's trunking each individual VLAN within that single gigabit connection. On the router side, we've configured 3 sub-interfaces for that Ethernet connection. Sub-interface G0/0.1, .2, and .3. And then we can assign IP addresses, subnet masks, and have completely different routing tables for each of these individual sub-interfaces as if they were physical interfaces on that router.
Now that I'm a mom, things are, well, different. I have twice as many outfits to plan.
There are many devices connected to the internet. Some estimates are 20 to 30 billion, and by the time you watch this video, it's probably, of course, going to be more than that. One of the challenges, of course, is that IP version 4 only supports 4.29 billion addresses, and we have completely exhausted our list of IP version 4. There are no more addresses or subnets to be handed out. So now we have to find some way to communicate across the internet to these billions of devices using a protocol with a relatively few number of IP addresses.
I put the Net Plus objectives in the chat so you can take a look at them and have them before tomorrow.
We often refer to that as being the way
I'll also drop them in the coursework for tomorrow because the class will open up tonight at midnight. And you're able to see everything.
Many different use cases. We just did this video.
If you have your measure ups for Net Plus, might be a good idea if you hadn't put them in yet, put in your key if you hadn't, and just make sure you can open up your Net Plus class and measure up. Or your Net Plus, make sure the course pops up for you.
18, which defines these different ranges of private IP addresses. These are IP addresses that are not routable on the public internet, so we most often use these inside of our homes and inside of our businesses, and we'll perform translation if we ever need to communicate out to the internet. Certain ranges of these IP addresses are probably already familiar to you. For example, one IP address range that is private is 10.0.0.0 through 10.255.255.255. In a large enterprise network, this is probably the IP address range that you're using. This RFC also allocates 172.16.0.0 through 172.31.255.255. And if you're using network address translation at home, you're probably using the IP address range of 192.168.0.0 through 192.168.255.255. So how are we able to take these private addresses, which we already know we cannot route across the internet, and somehow we are able to communicate to these internet connected sites? We are able to do this using network address translation. Let's take this example where Vala would like to communicate to the Professor Messer web server. Vala's IP address is a private IP address.
Oh, look who made it to the party. Hey, Zeus, y'all. He's in the building, y'all.
To a public IP address of 104.20.19.63.
How did you do? Let's give him a minute. He's like, nope, I'm just going to tell you now. Nope.
And the destination IP address of 104.20.
That's all right, man. That's all right. That's all right. That's all right. Take a deep breath.
With network address translation.
Just settle in.
This router knows that the source IP
take a deep
address
breath.
10.10.20.50 is an internal IP address, and we can't use this IP address if we want to communicate out to the internet. So this router,
I'm adjusting your hours right now for you, Jesus.
Address to something different. This router already has a list of IP addresses
Thank you, sir.
that could be used, and in this case, it's changed that IP address to 94.1.1.1. Now we have a public IP address, so now we can communicate directly to the Professor Messer web server. For this web server to communicate back to Vala, it's obviously not going to communicate back to the internal 10.10.20 address. Instead, it's going to reverse those IP addresses, and the source IP address now becomes 104.20.19.63, and the destination IP address is the 94.1.1.1 that was originally assigned by the network address translation router. When this router now receives that packet, it's going to perform the translation again, except in reverse, and modify that destination IP address to be the internal address of 10.10.20.50, which obviously matches the IP address of Vala, and now Vala has received that message from the Professor Messer website even though VALA has an internal private IP address. With standard network address translation, we are translating from one IP address to a different IP address. This means that if we wanted to have many people performing this translation,
Yep, Charles, you're okay. 7430.
Public IP addresses available. There's a way to make this much more efficient using a different form of network address translation called NAT overload or port address translation or PAT. Let's take that same example.
How far off were you, Jesus? You can sit in a private chat if you want.
IP address is 10.10.20.50, but you'll notice we'll also include the source port number, which in this case is 3233. The destination IP address is obviously the IP address of the Professor Messer web server at 104.20.19.63, and in this case, VALA is communicating to that server over port 80. When that packet is received by the router, it understands that 10.address needs to be translated to a public IP address, and inside of this router is a network address translation table that shows both the private address and the public address that it's translated to. You'll notice here that the private address of 10.10.20.50.3233 is converted to 94.1.1.1 with a port number of 1055. And when that translation takes place, our source IP address is now a public IP address, and that's what's received by ProfessorMesser.com. Because we're translating both the network address and the port number, other devices on this network could use the same public IP address. For example, let's take another scenario where we have Jonas at 10.10.20.70. Jonas's random port number that's used for this transaction is 5782. And of course, the destination IP address is the same as the ProfessorMesser.com web server with a port number of port 80. When that packet is received by the network address translation router, it knows that that address has not been used before, and it puts that into the network address translation table with a different port number on the public IP address side. So now we're using the same IP address of 94.1.1.1 as our public IP, but notice that the port number has incremented by 1. This means that we can now have many people on the inside of our network communicating externally to a server, all using the same public IP address.
Responding to emails takes time, but not with Grammarly. In a few clicks, Grammarly's generative AI drafts professional, relevant replies that sound like you. Download it for free at Grammarly.com.
Got pet odors? Get Febreze fabric spray to keep your fabric smelling fresh and clean.
As a very broad description, a local area network, or a LAN, is a group of devices that are in the same broadcast domain. For example, when we connect devices to a switch, all of those devices are in the same broadcast domain. In this diagram, we have one switch on the left, that's our red switch, and all of the devices connected to that switch are in the same broadcast domain. On the right side is a blue network. This blue network is also on its own switch, and all of the devices connected to this switch are on their own broadcast domain. Because there are two separate switches, and these switches are not connected to each other, no one on the red network can communicate directly with anyone on the blue network. One of the challenges with this configuration, however, is that we have two devices on the red network and two devices on the blue network, but you can see that there are 24 interfaces on the front of each of these switches. This means we're running two separate switches with two separate power sources. They're both taking up space within our rack, and we have to manage each of them individually. It would be much more efficient, much easier to manage, and much less expensive if we could have all of these devices reside on the same physical switch. We can do exactly that and continue to provide that separation between the red network and the blue network on the same switch by using a functionality known as virtual local area networks, or VLANs. The red network is still on its own broadcast domain, and the blue network is on its own broadcast domain, but all of these devices are connected to the same switch. We've gone into the switch and defined each interface on the switch as belonging to either the red VLAN or the blue VLAN. And devices plugged into the blue interfaces would be able to communicate with each other, and only the devices plugged into the red interfaces would be able to communicate with each other. Instead of colors, VLANs are defined by number. So in this switch, we have a VLAN 1, a VLAN 2, and a VLAN 3. We can see that there are devices that are connected to interfaces that are configured for VLAN 1, other devices connected.
I think it will be safe to say as of in the next 15 minutes, 5:30, everybody would have passed this course.
Communicate on VLAN 3. This becomes a bit of a challenge.
Y'all make me work for my money.
Connect VLANs across individual switches.
So good job for those who had to dig in.
Has a VLAN 100 and a VLAN 200.
You did it.
And the other
Thank you.
Also has a
And
VLAN 100 and VLAN 200.
I know some folks have had some challenges, so thanks for working around that too. It takes a lot to be here at this grueling pace of this program. So I know everybody, including myself, I got stuff going on too. Everybody's got something going on, but it's what you prioritize to make sure it gets accounted for, right? So you can move forward. So that takes a lot. Diligence. One takeaway that I would say when we move into Net Plus though, material is only going to get a little harder. I'm not saying it's not understandable. I'm just saying it's going to be a little harder as far as understanding a lot more terminology. So I would encourage for Net Plus, it's 3 weeks.
Instead of having
3 weeks.
multiple Ethernet connections between VLANs, we have a
Don't procrastinate.
Ethernet connection between these two switches.
If you can get ahead, do it.
Trunk interface.
If you can knock out the final exam in the first week, do it. Like this, get ahead. So if something does come up, you're not waiting until the last minute to try to get it done. Or because life happens sometimes. You don't know what's going to happen. I don't know what's going to happen. But at least you're kind of prepared for it. And being here, as much as you can be here, because one lesson could be like 2 or 3 questions that you possibly get on the exam, and if you don't know how to answer it, you're just kind of like, I don't know what happened. So, with that being said, we're good. You guys are good, though. You guys are good. I'm pleased with where your knowledge base is right now. Everything else will catch up. So, I think I was telling Martin today, if you didn't pass the exam, don't stress about it. The more you stress about not passing the exam, the more you push the information away from you because you're trying to force it in your brain. Just chill. Relax. Let your mind relax. When you're relaxed, you'll start hearing stuff that you didn't pay attention to before, and it might be that one thing that bridges something else to something else, and you're like, you're on your way, right? So it's just an exam. It's just an exam. You know, we'll do some tutoring. We'll talk. We'll get you there. Yeah. We got 45 more minutes. We're good. Unless you have to go. I know Charles has yes, an appointment. So,
VLAN 200 on one switch to a VLAN 200 on the other switch. We'll start with a normal Ethernet frame from a device that is connected to an interface defined as VLAN 200. This packet needs to find its way to a device that is on the other switch on VLAN 200, so that packet will be sent to the trunk interface on this switch. At that time, an additional tag will be added that includes the VLAN 200, and it is sent across that trunk connection to the other switch. The switch that receives that frame will look at the tag, see that it was destined for VLAN 200, it will remove the tag from the frame, and send that traffic to the end station. So now we have a much more simplified design. Instead of having a separate cable that's running between switches for VLAN 1, VLAN 2, and VLAN 3, we can have a single Ethernet connection between those two and simply trunk all of the traffic between those switches. When you first configure a switch, there will be a default VLAN for this switch. That means that every device you connect to this switch by default will be connected to a VLAN. Very commonly, this is VLAN 1 that is defined as the default VLAN. But there's another type of VLAN configuration that you would have inside of a switch known as a native VLAN. A native VLAN is one that can traverse a trunk, but a VLAN tag is not added to any of the traffic going over that connection. So it's common to define a single native VLAN within a switch that will never be tagged as that traffic is sent over that trunk connection. This is because there are some devices that will not communicate over an 802.1q network, and some of the administrative functions within your switches, where switches are communicating with each other, may need to use the native VLAN to perform that communication. For example, management traffic or switch notification messages may use the native VLAN rather than being tagged as a separate VLAN inside of that switch.
This is the newly redesigned Dell AI PC with Intel inside. It's not just an AI computer.
If you're defining a native VLAN on one switch, you'll need to make sure that that native VLAN is identical on the other switch that you're connecting to. Otherwise, you'll see error messages appear in the log of your switch. Up to this point, we've been describing a traditional layer 2 switch, that is referring to the OSI layer 2 or data link layer, where switches make their forwarding decisions based on the MAC address of an Ethernet frame. But there's another type of switch known as a layer 3 switch that's able to make forwarding decisions based on the OSI layer 3 or network layer of an IP packet. This is looking at the destination IP address and making a routing decision on where that traffic should go. You're effectively taking switch functionality at layer 2 and router functionality at layer 3 and combining both of those into the same unit. With the layer 3 switch, we're not changing the switching process. The switch is still operating at layer 2, and we're not changing the way that a router operates. The routing functionality within this device is still operating at layer 3. But both of these are now combined within the same device, saving space, saving power, and making the administration process that much easier. This means that we can have layer 2 functionality within our switch, where we might have separate VLANs within the same physical switch. But now we can also have routing functionality that allows us to route between those VLANs all within the same switch. This means that we'll need to configure interfaces inside of the switch that are designed to route from one VLAN to another. We refer to these as SVIs, or Switched Virtual Interfaces. If you have a layer 3 switch, it may not have the layer 3 functionality turned on by default, so you may need to enable that in your switch configuration. Many switches require you to restart the switch once you make that configuration change. And you may be thinking, why don't we use layer 3 switches for everything? Instead of having 2 separate physical devices, it seems that having one single physical device would be much easier to manage. And in many cases, that's true, but the routing functionality of a layer 3 switch tends to be less capable than the routing functionality of a standalone router. There is a term within the industry where we tell the switch needs to switch and a router needs to route. When you start combining those devices together, you begin to lose functionality. So if you have a smaller remote site, or perhaps even an internet router at home, you might have this layer 3 switching functionality to be able to route and switch within the same device. It's very common on our corporate networks to need both data functionality for our computing devices and voice functionality to be able to make telephone calls. Before the days of voice over IP, we would need to run one cable for our Ethernet network and a separate cable for our telephones. Our Ethernet cables would connect to a switch, and our telephone cables would connect to a PBX, or a private branch exchange. With the advent of voice over IP technologies, we can get rid of that individual voice cable completely and run both voice and data over the same Ethernet connection. And in many enterprise environments, you have a switch that is on the network, you have telephone that you would connect to the switch, and on the back of the telephone is an additional Ethernet cable where you can plug in your local computing device. One of the challenges that comes with adding both voice and data to the same network is that you now have a great deal of contention between both of those technologies. Data likes to use a lot of bursty bandwidth on the network, but voice communication prefers a very consistent level of access. If there's any type of congestion or a lot of usage on the network, this could affect the voice over IP communication, and none of your phone calls would sound very good. To resolve this issue, we can put our voice communication on one VLAN and put our data communication on the other VLAN. But of course, we're using a single wire to connect both our phones and our computers, so we can use VLAN technologies to do that within that same cable through the use of trunking. This requires you to use a switch that will recognize that you're connecting both a phone and a computer at the same time, but once you're using the right equipment, this becomes a relatively straightforward process. So now with this switch configuration, we can assign our phones to be VLAN 200, assign our computers to be VLAN 100, and send all of that traffic to our switch, where it will be able to break those two apart and put them on the correct VLAN for that particular use. This means we can now download as much information as we'd like from our computer while we're on the phone communicating with others and be able to perform both of those seamlessly.
Thank you for calling Capital One.
My team's GenAI tool helps you answer customer questions faster.
We use RAG with LLMs and customize them with our data for better accuracy. That's all we have.
That's technology at Capital One.
When you're configuring a router interface, a switch interface, or an interface that's in your local computer, there are a number of options available. In this video, we'll look at some of those interface configurations. We can start with the basic connectivity that we have to the network. When we plug in an Ethernet cable, there are a number of Ethernet settings we need to consider, and two of the most important are the Ethernet speed and the duplex. The speed is obviously going to be how fast this connection is going to run. This might be a 10 megabit connection, 100 megabits, 1000 megabits, which would also be 1 gig connection, 10 gig, or even faster. We have to be sure that this configuration is the same on both sides. So if we have a computer that's connecting to a switch, the speed on both of them has to be configured the same. In many cases, we would set this to automatically configure itself. So you can simply plug in any device and the switch will automatically adjust to the configured speed. The other option we might have available is either half duplex or full duplex. In most cases, this is also set to automatic. But if you do set these manually on both of these devices, you have to make sure that both of them are set to be the same. If you have the speeds mismatched on both sides, the connection will not work at all. You'll never get a link light. But if you mix the duplex configuration, where one side is set to half duplex and the other side is set to full duplex, you'll find the connection does operate, but you'll notice that it is not quite as efficient as it should be. And in fact, you'll have very poor performance if you start putting a lot of traffic over that link. This is why one of the initial configurations we'll look for when we're troubleshooting Ethernet is the speed and the duplex, and make sure that they're the same on both sides of the connection. If those match, then we'll shift our focus to the Internet Protocol, or the IP configuration for that interface. This might be an Ethernet connection, it might be a VLAN config, we might be setting up management interfaces, and all of these will need an IP address, a subnet mask, a default gateway, and perhaps other IP configurations as well. These will usually be values that have been assigned by a network administrator. So we'll want to configure and make sure that the IP address, subnet mask, default gateway, DNS settings, and everything else matches the configuration that we've received from our admin. If this configuration doesn't match what we've been given, let's say we've used a different default gateway IP address, or we put in the incorrect subnet mask, then we may find that we're not able to connect to other IP devices on this network. Fortunately, this is a relatively easy configuration to validate. We can simply look at what we've been given and look at what we've configured in the system and make sure that both of those match. Another useful configuration, especially between switches, would be one for link aggregation. This is sometimes referred to as port bonding, or you might see it abbreviated as LAG for link aggregation. This means that we are connecting multiple interfaces together on these two devices, which normally we would not want to do because we would be creating a loop. But if you've configured all of those interfaces as link aggregation, the switch will interpret them as one very large connection rather than 4 individual connections. So if all 4 of these were gigabit Ethernet connections between the switch, we would configure those as lag, and you now have 4 gigabits of throughput to be able to communicate between those two devices. Some switches will support an automatic configuration of this link aggregation using a protocol called LACP. This is the Link Aggregation Control Protocol. This allows you to simply configure the interface as LACP, plug in the interfaces, and all of the underlying link aggregation configs will automatically configure themselves between those two devices. If you were to capture traffic between these two devices, you would see LACP traffic being transferred from one switch to the other. To be able to have the most efficient communication from one device to another, we need to be able to send packets across that will not be fragmented along the way. Since we don't always know what networks are located between the two devices, there may be times when our data is fragmented and therefore is less efficient to transfer across the network. Fragmenting a packet tends to slow down the overall communication, and if we lose one of those fragments, then we have to resend the entire frame again. Normally, the determination of the most optimal MTU, or maximum transmission unit, is done automatically when you first connect to a device. But sometimes filtering and firewalls won't allow the automated process to work properly, and you may need to manually configure an MTU on your system. On some networks, we're not trying to minimize the size of our communication. Instead, we're trying to maximize the size of our frames. And one of the ways we can do that is through a method called jumbo frames. Ethernet frames by default are 1,500 bytes in length. If we're transferring large amounts of data, we may want to increase the size of those frames to make the communication that much more efficient. And with jumbo frames, you can increase the size of an Ethernet frame up to 9,216 bytes of an MTU. On many devices, you'll find that they'll use 9,000 as the accepted high end of a jumbo frame. In fact, here is the configuration from my computer that says that I can configure frame sizes on my network to be between 1280 and 9,000 bytes. This means I can transfer a single frame that contains the same amount of information as 6 normal frames on the same network. This means there are fewer packets to have to switch or route through my network, and I can transfer much more in a shorter amount of time. The challenge, though, is all of the devices that are in that communications path must understand jumbo frames. So all of your switches, all of your routers, and the other devices you're communicating to have to also be configured to use these jumbo frames. If there's any device in the middle of this communication that doesn't understand jumbo frames, then they will drop these frames and you won't be able to communicate to that device at all.
Dear Friday, we've got power tailgates to power game days.
If you had 2 switches and you connected them together with an Ethernet cable, and then you connected another Ethernet cable to those switches, you would create a loop on the network. This means an Ethernet frame would loop around that particular connection until you disconnected one of those cables. There's no mechanism at the MAC address level to count how many times you've seen a frame. So as these frames are going around this loop, you're adding more and more frames to the network all the time. Those are continuing to go around this loop, and eventually you'll overwhelm the capacities of your switches. This can happen relatively quickly. Once you create a loop in a network, it might be a number of seconds until people start calling the help desk stating that the network is down. Fortunately, this is relatively easy to resolve. You simply go back to the switch where you plugged in that cable, you disconnect the cable, which removes the loop from the network, and now everything is back up and running. But of course, we're not always standing in the data center ready to plug or unplug a cable from a switch. We need some type of automated method to recognize a loop on the network and to prevent those loops from occurring. Fortunately, we have a standard that's able to recognize and prevent loops on a network. This is the IEEE 802.1d standard, one that we call the spanning tree protocol. Spanning tree can configure interfaces on our switch in a number of different ways. It may configure the switch port to be blocking, which means it's not going to forward any traffic. This is commonly used to prevent loops on a network. If we were to plug in that second cable to our switch, Spanning Tree would recognize that a loop was being created, and it would cause one of those interfaces to be in a blocking state. The listening phase is used by Spanning Tree to clear out existing tables and restart the process. It's going to go through a learning process where it listens to understand where all of the other switches might be and if there might be any loops on the network already running. And then it will configure an interface to be forwarding, which means traffic can be transmitted through that interface, or will it configure an interface to be blocking. We might also have interfaces that are administratively disabled. Those obviously would not participate in this spanning tree process. Here's a network that is already running spanning tree, and there are a number of switches. They're identified as bridge 1, bridge 6, bridge 5, and so on. You can see there are 5 of them in this particular design, and you can see that many of these switches are connected to each other, and if we didn't have spanning tree running, there would be a loop on this network already. But on this network, we already have spanning tree that's operational, and it has configured a number of different interfaces. There are 3 different types that you can see on the screen. One is the root port, or RP. This is the interface on a switch that is connected ultimately to the single root bridge on the network. There's also a designated port, which would be any other port that can forward traffic, but is not the port that is connected directly to the root bridge. And there are block ports. These are ports where spanning tree has disabled that port from sending or receiving any traffic. You can see on this network that bridge 21 has a blocked port and bridge 11 has a blocked port, and those have been blocked so that there is not a loop on the network. If we were communicating from bridge 11, you can see there is a single root port, and you can follow that all the way back with those root ports to the final root bridge. The designated ports are also available to be able to send and receive traffic. In this scenario, let's say that we're on network A and we've been communicating with a device on network M. You can see that we can communicate through bridge 6, which has a designated port and a root port that allows us access to network M. But what if there is a problem on this network and we lose connectivity between network A and bridge 6? Now we need some other way to communicate to network M, but as you can see, there is a blocked port on bridge 11, so we would not be able to communicate through that connection. Fortunately, spanning tree recognizes that we have this disconnection, and it begins clearing out the existing configuration and relearning the topology of the existing network. Spanning tree has changed bridge 5 so that the root port is now on the other side, and it has removed the block port on bridge 11, allowing us on network A to be able to now communicate all the way through the network back to network M without having another loop on the network. On many networks, we do talk about enabling spanning tree and making sure that our spanning tree configuration is turned on inside of our switches, but in reality these days we're probably running a newer version of spanning tree called the Rapid Spanning Tree Protocol. This standard is the 802.1W standard. In the original spanning tree protocol, it might take 30 to 50 seconds for the convergence process to occur. And on today's networks, that is a very long time to wait without any type of connectivity. With Rapid Spanning Tree Protocol, this convergence process goes down to about 6 seconds, which means anytime there's a disruption on the network, we can be back up and running relatively quickly. Fortunately, this Rapid Spanning Tree Protocol is backwards compatible with the original spanning tree, so if you have a mixed set of devices on your network that support one or the other standard, you can run them all at the same time. Fortunately, Rapid Spanning Tree Protocol works very similar to the original spanning tree configuration. It simply operates much faster. There are some shortcuts and other configuration settings within the Rapid Spanning Tree Protocol, but it has such familiarity that if you understand Spanning Tree Protocol, it will be very easy for you to understand the details of Rapid Spanning Tree Protocol.
Wait, is this you when trying to build a website? Because I got you.
Oh, check out Bluehost. They have an AI site creator that makes it a breeze. Build your own professional looking site in minutes. All you have to do is type in some details about your business, and the AI site creator will generate 3 awesome designs for you to start with. Then you can customize it as much as you want. Add in your pictures and branding colors, and boom, fully fledged site is up in minutes. You didn't even have to code anything. This is perfect if you're trying to get your site up in time for the home.
We've become so accustomed to wireless networks being available that we often forget that there's a lot of work that happens behind the scenes to create these wireless connections. This work is done primarily by the Institute of Electrical and Electronics Engineers, or the IEEE. There's a committee in the IEEE called the 802.11 Committee, and that is the committee that focuses on creating worldwide standards for wireless networking. In the past, we've referred to the standards name to be able to describe the network. For example, we'll describe 802.11ac, 802.11ax, or 802.11be. The IEEE committee realized that these numbers and letters combinations weren't very appealing for most people, so they've also assigned separate names that are a little easier to keep track of. For example, 802.11ac is Wi-Fi 5. 802.11ax is Wi-Fi 6 and Wi-Fi 6E, the extended version of Wi-Fi 6, and 802.11be is also called Wi-Fi 7. As additional major releases of the 802.11 wireless standards are released, they will also increment those Wi-Fi numbers, so in the future we should see Wi-Fi 8, Wi-Fi 9, and so on. There are a number of technologies used by 802.11 wireless networking, and the first is the frequencies that are in use. 802.11 commonly uses 2.4 gigahertz, 5 gigahertz, and 6 gigahertz frequency ranges. Sometimes there's a combination of those. You may have an access point that supports both 2.4 and 5 gigahertz, and some access points may support all of those frequencies at the same time. Instead of having to memorize individual frequency numbers, the IEEE has created groupings of these frequencies known as channels. These channels help us easily understand what frequencies we may be using. For example, on this access point, we're using both the 2.4 gigahertz range and the 5 gigahertz range. The 2.4 gigahertz range is using channel 6, which is centered on 2.437 gigahertz, and the 5 gigahertz band is using channel 44, which is centered on 5.220 gigahertz. You can see that referring to this as channel 6 is much faster and more efficient than saying that this particular access point is centered on 2.437 gigahertz. The amount of frequency that we use is referred to as the wireless bandwidth. And when I say that channel 6 is centered on 2.437 gigahertz, there's actually more frequencies that we're using for that single channel. Different frequency bands have different sizes of bandwidths that can be used, but it's very common to see 20 megahertz, 40 megahertz, 80 megahertz, and 160 megahertz bandwidths. Here's a diagram that shows the 2.4 gigahertz range, the 5 gigahertz range, and the 6 gigahertz range that's used by 802.11 wireless networks. We'll start with the 2.4 gigahertz spectrum. You can see there are 3 non-overlapping channels in that particular range, and it's using the 20 megahertz bandwidth to describe those 3 channels. Next is the 5 gigahertz spectrum, and you can see there are many more frequencies available in the 5 gigahertz range. You'll also notice that we might use different bandwidths depending on the access point that we're using. So we might use anywhere from 20 megahertz to 160 megahertz, and you can see the ranges that are available for those particular frequencies. And in the 6 gigahertz range, we have even more frequencies available, giving us options to be able to transmit and use these wireless networks without conflicting with other wireless networks that might be nearby. As you can tell, there are many frequencies available to choose from for your wireless networks, but not every frequency is going to be the best one to use. There may be differences in the environment where you happen to be, where one frequency might work better than the other, or there may be other access points that are already using certain frequencies. You might also be using older devices that aren't able to communicate on the 5 or 6 gigahertz ranges and may only be able to communicate on 2.4 gigahertz frequencies. But if you have a modern wireless device, you might have options. Your phone, for example, may be able to support 2 or more different types of frequencies. It just needs to be able to choose the optimal frequency for where you happen to be. Your access points can be set up with a feature known as band steering. This allows you to specify how the users might be able to use the frequencies in the best possible way. For example, you might have a user that has a mobile phone, and that phone can support either a 2.4 gigahertz connection or a 5 gigahertz connection. And you might have access points that also support both of those frequencies. So which frequency does your phone choose when it's connecting to that access point? If band steering is not configured in the access point, the device will simply use the one that has the best possible signal. Sometimes that best signal will provide you with the best throughput, but that's not always the case. And you may find that you get better throughput using a different frequency, even though that frequency may not be the one that has the strongest signal. If band steering is turned on, the administrator of the access point can determine what frequency a user will choose if they have a choice. For example, if a user is connecting to an access point with band steering enabled, and that device can support either 2.4 gigahertz or 5 gigahertz, you can force it or steer it into using the 5 gigahertz frequencies by default. One of the challenges with these wireless networks is that each country makes its own decisions about how this wireless bandwidth is to be used. For example, in the United States, we have the Federal Communications Commission, and they are responsible for managing all of the frequency allocations in the US. Of course, the FCC can't control how other countries manage their frequencies, but they do work very closely with other countries around the world to make sure that everyone is properly managing these very important frequencies. Another challenge with this is that we are coming up with new technologies and new ways to use these frequencies all the time, and we sometimes have to make sure that different services can use similar frequencies without any type of conflict. The popularity of these wireless networks has almost required that all of these countries work together to come up with standards that everyone can agree on. A good example of these organizations working together can be found in the 802.11h standard. This adds a number of interoperability features to 802.11 wireless networks so that you can have many different wireless networks in one area, but still allow all of those networks to work together. There are a series of guidelines for wireless communications that are published by the International Telecommunications Union. The ITU provides a worldwide approach to managing these many different wireless technologies. One of the things that is included in these standards is called DFS. This is Dynamic Frequency Selection. This allows our wireless access points to use frequencies that are not going to conflict with other access points that may already be operating. This is one of the reasons that when you turn on your wireless access point today, that you don't have to manually configure any of the wireless settings inside of that device. It automatically looks at the frequencies that are in use and chooses a series of frequencies for you that are not going to conflict with anything that may already be operating. And if something does change with the wireless environment and your access point needs to change its channel, it will tell all of the devices on that network to also move along with the access point. Another interoperability feature is TPC, or the Transmit Power Control. Traditionally, we've set the power that we would use for these wireless networks on our clients, but TPC puts the transmit power control in the hands of the access point. This means that the access point can tell a client to use less power to be able to communicate over this wireless network. This means that we can have many devices communicating at their optimal power level without having any type of conflict with other third-party services.
The industrial-grade products you need, delivered fast. Call, click, or stop by. Granger.
When we think about wireless networking, we often think about connecting to an access point. But of course, you can communicate directly to another device without an access point. We refer to this as Independent Basic Service Set, or IBSS. You might also see this referred to as an ad hoc connection. This allows us to configure one device as an ad hoc connection, configure the other device as an ad hoc connection, and simply connect those two devices to each other over those wireless frequencies. You might have used this functionality when you've configured an Internet of Things device, such as a door lock or lights in your home. This is a way to connect to a device over an ad hoc connection, provide that device with information about your existing wireless network, and then have that device connect directly to the access point. And in most environments, we have an access point that many different devices are connecting to be able to network everyone together. Behind the scenes, we're using different parameters to configure this device. Two of those parameters are the SSID and the BSSID. SSID stands for the Service Set Identifier, and it's the name of the wireless network that we're connecting to. So you might have an access point with an SSID of SGC1, and when you bring up the list of all of the available access points in your area, you will see that SSID name appear in your list of available networks. Of course, this same SSID might be configured on multiple access points, especially if you have a very large home or you're in an environment where there are multiple areas of the building and you want to have wireless connectivity wherever you might be in that building. To be able to differentiate between one access point and the other, we need some type of hardware address on that access point, and that hardware address is known as the BSS ID. This is the basic service set identifier. So although there is a wireless network name that we see, such as SGC1, there's also a hardware address that we normally do not see behind the scenes. In this case, this wireless access point has a BSS ID of 603 Delta 26112233. As we've already mentioned, in your home or a very large business, you may have tens, hundreds, or even thousands of access points to manage. All of these access points need to be able to work together so that as you are passing from one building to another or from one area of the building to the other, you're able to seamlessly move from one wireless access point to the other. This is often done by using the same SSID or wireless network name on each of the wireless access points. We refer to this shared network name that's used across access points as an ESSID. The E stands for the Extended Service Set Identifier. With the ESSID configured across all of these different access points, you can start on one end of the building, walk to the other end of the building, and you will be moving automatically and seamlessly from one access point to the other. Here's a configuration that uses ESSID to provide that seamless roaming from one access point to the other. In the middle at the top, we have a network switch. This switch has an Ethernet connection to an access point on the left and an access point on the right. And you can see that the BSS ID, or the Basic Service Set Identifier, which is the hardware address of the access point, is different on this access point than it is for the other. Although these are obviously two different pieces of hardware, they are sharing the same SSID. You can see it's configured as SGC1 on this access point, is also configured as SGC1 on the other access point. As we move outside the range of one access point and move into the range of another access point, that access point will automatically pick up that we are nearby and seamlessly connect this device to that same SSID without any notification on your mobile device. This means you can continue to surf the internet, transfer files, and use the network normally, even if you happen to be moving at the same time. When you first connect to a wireless access point, you may be prompted with a screen that gives you information about the network or requires you to authenticate to gain access to that network. We refer to this screen that appears and the prompt with the authentication credentials as a captive portal screen. For this captive portal to work, there is a centralized access table that identifies individuals that are already authenticated to the wireless network. And if it notices there's a new device that has not previously authenticated, it will present this captive portal screen to the end user. On the captive portal screen, there may be a series of terms that have to be agreed to, or it may prompt for a username, a password, or some other type of authentication factor. If those credentials are entered properly, then that information is added to the access table and you gain access to that wireless network for a predefined amount of time. For example, your captive portal may be good for 24 hours, and at the end of that 24-hour period, you have to re-authenticate to gain another 24 hours of access. There are many different ways to configure security on a wireless network. And if you look at the configuration of your access point, you may find that there are a number of different options that you could choose from. For example, on this access point, the security level is currently defined as WPA2 personal. This access point can also disable security. It can configure a security mode on this access point known as OWE, which stands for Opportunistic Wireless Encryption, which effectively allows someone to connect to the wireless network but prevents them from communicating directly to any other wireless device. This access point also supports WEP, different flavors of WPA, WPA2, and WPA3. An open system, of course, means there is no security, there is no authentication process, and anyone on this wireless network can communicate to anyone else on this wireless network. This access point supports WPA, WPA2, and WPA3 using a personal type of security. Sometimes you'll see this referred to as PSK, which stands for Pre-Shared Key. This means to gain access to this wireless network, we need to provide someone with a pre-shared key that everyone will use. For example, you may be at a coffee shop and there may be a notice at the coffee shop that the pre-shared key that everyone can use to access the network is hot coffee. Of course, if you're in a business environment, having everyone share the same password for the wireless network is inherently insecure. So most enterprises will use a different type of wireless security known as
I'm hosting a tournament.
We have to win.
Cowabunga.
enterprise or 802.1x security. This allows the network administrator to require a username, password, or some other type of authentication to gain access to the wireless network. And most people will use their own personal credentials to be able to provide that access. This means you would use the same username and password you would normally use to log into other devices in that same enterprise network. This means if someone leaves the organization and their account is disabled, they no longer have access to that wireless network. If you look at the different antennas that are used on many of today's wireless networks, you may notice a number of different styles. The style of antenna that you see connected to this access point is an omnidirectional antenna. It's a very common antenna type to find on our consumer or home-based access points. An omnidirectional antenna will evenly distribute that wireless signal on all sides of the antenna. So you can put your access point in the middle of the room, and everyone in the room will have the same signal strength as everyone else. This means you can put your access point in a centralized area, and anyone who's nearby will be able to gain access to the wireless network. But this may not be the optimal antenna type to use. For example, your access point may be in the corner of an outside room, and you're effectively only seeing a portion of that signal, while the rest of it on this omnidirectional antenna is sent to places where no one will ever connect. In that scenario, you might want to use a directional antenna, where you can take that wireless signal and send it into a single direction. This allows you to focus the transmission and receiving of wireless signals to a device that may be in the corner of a room or may be connecting different buildings to each other. You'll often see these antennas measured as a total number of decibels. For example, a directional antenna may increase the performance of that signal by a certain decibels of gain. For example, you may see in the specifications of a directional antenna that it effectively increases the overall power by 3 dB. And for every 3 dB, we are effectively doubling the amount of power available. One type of directional antenna is a Yagi antenna. This is an example of a Yagi antenna. It is very directional and has a very high amount of gain. We also have other directional types such as a parabolic antenna, where multiple signals can come in and bounce into a single feed horn in the front, so it's focusing all of those signals into a single point on the antenna. This is especially useful over longer distances where you need to collect that signal and focus it into a single spot. Most of the access points that we use at home are autonomous access points. This means that the access point doesn't require any type of additional hardware or software to be able to operate. It's effectively a standalone device that doesn't rely on anything else to be able to maintain that wireless connectivity. But in an enterprise, you may not be using autonomous access points. Instead, you may be using lightweight access points. This separates the wireless functionality into the hardware that you would mount into the ceiling, and the configurations and intelligence of that device are often maintained on the switch the access point is connected to. This not only allows us to have less expensive access points that we can deploy, it also gives us functionality for being able to manage those devices. One standard for managing wireless access point is known as CAPWAP. This is control and provisioning of wireless access points, and it allows you as the network administrator to manage and configure all of these wireless access points from one central management station. We refer to this central station as a wireless LAN controller. It allows us to connect and view the entire wireless infrastructure from one single screen. We often refer to this as a single pane.
Ryan, did you want to go back and retest this week?
From the management station, we can deploy new access.
Since you were close.
We can monitor the performance of our existing access point infrastructure. We can make changes to the
Wanna go back Friday?
configuration of our wireless network and deploy those changes.
All right, I'm gonna cut you off real quick. Can you add that up real quick?
Access points.
Okay.
And this might also create reports showing us how much of the wireless network is being used and by whom. This wireless LAN controller is often paired with the wireless access points themselves, so you're often getting the access points and the wireless management station all from the same manufacturer.
Coach here to tell you about an all-star bundle. It's Disney Plus, Hulu, and ESPN. And right now you can get all three with a special limited time offer. It's as easy as
There are a number of different ways to connect and configure wireless networks, and in this video we'll look at some of these different wireless network types. One popular wireless network type, especially in home-based environments, is a wireless mesh. This is where you would have multiple access points that can all communicate to each other within a relatively close area. And then you would have other devices that are located on the outside of those access points that are able to communicate to that single access point and ultimately to the rest of the network. This meshing of access points in the middle is something that you would configure on the access point, and if you were to add additional access points onto this network, they would also be included in that same mesh of access points. Of course, this doesn't have to be access points. There are some devices that can mesh amongst each other in an ad hoc.
Just send it to you in the
This
chat.
allows for different options for sending data over these networks because all of these devices are now communicating.
Let me know what time
with each
you're
other.
going
And
Friday.
if one device leaves the network, it can automatically identify that that device is no longer there and self-heal itself to maintain connectivity to everyone who's left on the wireless network. If you only have two devices, you might want to connect them together without an access point. We refer to this type of connectivity as an ad hoc connection. This is where you would use the 802.11 wireless functionality of your device, but you would not be directly connecting to an access point. This uses the 802.11 wireless network functionality of this device, but instead of connecting to an access point, you simply connect to the other wireless device. You might also see this referred to as an independent basic service set, or an IBSS. This might be something that is a very long-term connection. If all you have are two devices, you can simply connect those two together and they will communicate as long as that connection is available. But you might be using this on more of a temporary basis. This might be used in conjunction with an Internet of Things, or IoT device, where you would initially connect to the IoT device over an ad hoc connection. This may allow you to transfer configuration details, such as the name of your larger wireless network and any security configurations that have to be included to connect to that wireless network. At that point, the ad hoc connection is then disabled, and the Internet of Things device can connect to the larger access point network using those configuration parameters. Some wireless access points allow you to connect two devices directly to each other over a point-to-point mode. The point-to-point mode is commonly used to connect larger distances to each other. For example, one building connecting to another building. I run this exact configuration between two homes, so you could have an access point in one house connected to a switch and all of the internal devices of that network connected to the same switch, and then you would have the same configuration in another home and have all of those networks now connected to each other.
All right, everybody, we are at 6. I'd like to congratulate everybody. From what it appears to be, everybody has passed 12 hours of GPA. That's the first hurdle we got to get over. That's the one I like. Everything else we can work on. Tomorrow we start Net Plus. And if you don't have anything from me, I will see you in the morning. And we will get going on that. And I'll hang out with Brian here until it gives me a time. But everybody else have a great evening.
Common way to connect to a
See you
wireless
then.
network is in something called infrastructure mode. This is where you would have a centralized access point. And this
So they
is
didn't have
probably
an
the type of
appointment till
wireless
the
network
23rd.
that you're using at home and
So-
in your office. All of the wireless devices in your home or office connect to that central access point, and you're able to communicate out to the wired network or between other wireless devices over that same access point. Some wireless access points keep